Today, what happens when you fall into a black hole? A black hole appears when an extraordinary amount of matter is concentrated in a tiny space. So how this happens? During a supernova, a highly massive star undergoes a cataclysmic explosion, leading to the implosion of its core under the overwhelming force of gravity. The intense pressure forces atomic nuclei and particles to collide, causing electrons to merge with protons and transform into neutrons. The empty space within atoms is suddenly filled with particles, which repel each other but have no other option but to remain in close proximity. They desperately push back against gravity, against the collapse. If gravity wins, they will become a black hole. If they win, they become a neutron star. Well, this is another story. At the center of a black hole, gravity is so incredibly intense that anything that ventures too close is torn apart into its fundamental particles. The gravitational pull is so strong that not even light can escape, resulting in a sphere of complete darkness that we perceive as a black hole. The surface of the black hole is called the horizon of the black hole. Today, we understand that our universe is home to many black holes, which are typically located far from us and pose no threat. Despite this, the question of what we might see if we were to fall into a black hole, out of curiosity, remains a fascinating one. Exploring this question could enhance our understanding of extreme phenomena that exist in the universe. Our Milky Way galaxy is home to a colossal feature at its core, a supermassive black hole, named Sagittarius A star. It may be incredibly distant from us, but let's imagine for a moment that we managed to travel there via spaceship, and let's see what happens until the end. As we approach this monstrous object, we can't help but feel a sense of both excitement and terror. After reaching the vicinity of the black hole, we jumped out of the spaceship. We are first met with a striking sight, the thick disk of plasma that orbits around it. This is called accretion disk. Within this disk, dust and gas swirl around chaotically. How this happens though? Well, this phenomenon is driven by the black hole's immense mass, which is millions of times greater than that of our Sun. Such a colossal object exerts an irresistible gravitational attraction that captures surrounding matter, including massive stars. When a star comes too close to the black hole, the star is eaten, and the black hole is fed on. This spectacular event is known as a tidal disruption flare, and is believed to be a rare occurrence, happening maybe once every 10,000 to 100,000 years within a galaxy. As the star approached the side closest to the black hole, it experienced a vastly greater gravitational pull than on the other side, resulting in the star being torn apart into shreds. The matter from the star then began spiraling into the black hole, forming an accretion disk. Well, to continue our journey, we will face challenges because this annular ring made up of a gas and dust is accelerating and heating up, generating intense radiation. The radiation emitted includes visible light, ultraviolet radiation, and X-rays. Those lights could blind us instantly. An accretion disk is also very hot, with talking to millions of degrees, which might burn us alive too. Moving forward, let us assume that we are equipped with a highly advanced spacesuit that is specifically designed to withstand the intense heat and radiation of the environment surrounding the accretion disk. As we passed through the accretion disk, the gravitational force became even more intense. As we continued to approach the black hole, something strange started to happen. Despite the fact that we were getting closer and closer, the black hole itself seemed to be moving away from us at an increasingly rapid pace. We are falling at a dizzying speed of 4% the speed of light, hurtling towards the unknown with reckless abandon. There is also an interesting phenomenon which catches our attention. If we were to turn around and look back at the clock inside the spaceship, we would notice that it seems to be running slower than before. This subtle yet noticeable effect is a result of time dilation, a consequence of the intense gravitational forces that we are experiencing. The closer we get to the black hole, the stronger these forces become, and the slower time seems to be passed for us. Minutes pass, and we finally fly over the disk of matter. After falling for about an hour, the glowing disk suddenly starts to fade out. This means that the matter can no longer orbit the black hole steadily, because the gravity is too strong. The plasma quickly spirals into the black hole, disappearing from view. As we explore the space between the accretion disk and the black hole, you will notice a specific distance where the accretion disk appears to end before reaching to black hole's surface. So why is that? This happens because there is a specific point. It's called the innermost stable circular orbit, also called as the ISCO, with a radius known as r-ISCO, that matter can maintain around a black hole. For most black holes, this orbit lies at a distance of 3 Schwarzschild radii. So then, the ISCO radius is 3 times the Schwarzschild radii. This is closest possible orbit for matter to maintain around a black hole. If it falls inside this orbit, it rapidly spirals towards the black hole's center and is lost forever. We never receive any information or signals from it again. In just 3 minutes, we will have moved twice as close to the black hole's surface, the point of no return around the black hole. But you will notice that there is something that can orbit closer to the black hole, and that is light. Because light has no mass, it can actually orbit at a 1.5 Schwarzschild radii. Beyond this point, any light coming from outside is inevitably drawn towards the singularity at the center of the black hole. This boundary is called the photon sphere. So we are standing at photon sphere, and looking forward, we would see the back of our head, because photons would be able to complete an orbit around the black hole and return to our eyes. However, this orbit is unstable, meaning that eventually the photons will either spiral into the black hole's singularity or escape and travel off to infinity. Therefore, it would be a short-lived experience to observe the back of our head from this vantage point. As we approach, the passengers who remain on the spaceship, they will see our image fade and slow down until it freezes on the horizon. The light we emit will take more and more time to escape the black hole, gradually becoming dimmer until it eventually fades away. Unfortunately, the passengers will never see us cross the horizon due to this gradual fading and slowing of our image and light emission. But what if we chose to turn back before passing the photon sphere and return to our spaceship before it's too late? Beware, for the black hole's gravity has a sinister surprise in its store. Our return journey may take us eons into the future, leaving us stranded in a strange and unfamiliar time where our loved ones are long gone. But if we continue our journey, in just 3 seconds after crossing the photon sphere, we will reach the point of no return, the horizon. After this moment, it will be impossible to escape the black hole's grasp, and we will be sucked into its maw. Any chance of returning to the life we knew before will be lost forever. So, what do we see after crossing the horizon? Despite our expectations of mind-bending spectacular upon crossing the horizon of a black hole, the reality is far less dramatic. In fact, there is nothing particularly special to see as we cross the horizon. There are no visible signs, no sudden changes in the environment, and no strange phenomena that can be observed. In fact, it would be incredibly difficult to determine the exact moment we crossed it. We can still perfectly see our body, in particular our feet, because even light is trapped and pulled inward by the black hole's immense gravity. Some photons can still escape and move upwards, allowing us to catch a glimpse of ourselves in this strange and terrifying environment. This is all due to the curious curvature of a spacetime that occurs when in the presence of such a massive object. At a local level, everything appears normal and behaves according to the laws of physics. But on a global scale, space-time is warped, and objects inside the event horizon are cut off from the outside world, creating a boundary beyond which nothing can escape. Here inside the event horizon, space and time are twisted beyond recognition. creating a bizarre landscape where time travel becomes even a possibility. But don't let that fool you into thinking you could escape this crushing grip. Any attempt to move in any direction, even forward, will only lead you faster to the center of the black hole. To survive the longest, the only strategy is to do nothing and await your fate. The event horizon may seem terrifying, but it's also a barrier that keeps the rest of the universe safe from the catastrophic consequence of time travel paradoxes. However, starting now, any attempt to transmit a signal outside our location will be futile, as the signal will never successfully reach its intended destination. Although we appear to be safe for the moment, our journey towards the center of the black hole is not over yet. As we approach the singularity, located about 30 seconds away, we must prepare ourselves for the imminent and immensely powerful force that awaits us. In an instant, this force will stretch and contort our bodies in a process known as spaghettification. It is important to note that this phenomenon lasts for approximately 30 seconds in a supermassive black hole, like the one at the center of our Milky Way galaxy. However, for a smaller black hole, spaghettification is only a risk, and we are unlikely to last that long, as they have much smaller radii. I mean, straight to the center after crossing the horizon. So after 30 seconds, a painful death by spaghettification awaits you. Welcome to the heart of darkness. Due to the intense gravity, your feet experience a much stronger pull than your head, which can cause your body to be stressed and pulled apart. As you descend further into the black hole, the pulling force gets even stronger and your body gets squeezed thinner and straighter until you are reduced to a long, thin stream of hot plasma. At this point, you are ultimately consumed by the black hole in one final slurp, and you disappear completely. Within a tenth of a second, the intense gravitational forces of the black hole shred the remains of our body into a long, thin stream of hot plasma that hurtles towards the center. At this point, our journey comes to an abrupt and final end. At the moment, the extreme conditions near the center of a black hole are beyond the reach of our current understanding of the physics. Our existing theories describe singularities, points where the curvature of space-time becomes infinite, but these concepts are limited and incomplete. In fact, science questions whether singularities even exist and believe that we must unify gravity with quantum mechanics to fully comprehend these extreme regions of the cosmos. Some theories even suggest that crossing the horizon could be fatal, as the singularity has no surface or size, much like an error in the universe. Ultimately, this is the extent of our knowledge based on the best prediction we have from our current theory of spacetime. Moreover, the black holes can have angular momentum, which can lead to the multiple horizons and mathematical instabilities that we have yet to fully comprehend. This is because most black holes in the universe were born from dying stars that were spinning extremely quickly in their last moments. As far as we know, all black holes in the universe should be spinning right now, at an incredible speed too, up to 90% the speed of light. I mean, what are the chances that a bunch of matter just collapses into a point perfectly with no rotation? It's just not going to happen. This means that black holes are even more bizarre and enigmatic than we typically give them credit for. Our current theory still gives us a good idea of what we would see if we fell into one of them.